Okay. Hi everyone, can you all hear me? So apparently we are having issues with our speakers here and my voice is still broken, so it's going to be a fun day. First of all, I wanted to ask if you have any questions about last lecture. So just to give you a quick recap, last lecture we were studying multiscale decomposition of signals with the hope that we could provide the orthonormal basis of the full space of square integrable functions, so with wavelet analysis, as opposed to the set of square integrable periodic functions, which we managed to approximate efficiently with Fourier decomposition. Okay, so here we are really trying to do something more difficult, capture accurately a much broader set of signals, which we consider in continuous time, with the hope that we can accurately compute on these signals, although we can only sample them at discrete time steps and also represent them at discrete time steps. So, sorry, I'm just having issues with that.
Can we increase the volume?
I don't. Can we increase the? Is there any way we could increase the volume within the room, or? Yeah. Okay. Sorry, I just cannot. Thank you. I cannot really speak louder than that. All right. So today I will rewind a little bit and try to delineate the great things about the dyadic wavelet decomposition and also some of its limitations, and also show you practically what it looks like when we take a certain input signal, well, this time in discrete time, and we decompose it across dyadic scales. And so by dyadic here, I just mean that at every step of the multiscale decomposition, I'm going to divide the resolution by 2. Okay, so I'm going to have twice as coarse a pixel set to represent my signals. So once I'm done with this set of examples, and particularly once I've shown how one of the advantages of multiscale decomposition is that we don't exactly have a prior now on the typical timescale at which two signals show a certain degree of correlation. So as we don't have this prior now, we can detect relationships between, say, stock prices, as these relationships can occur on the second scale resolution, but perhaps also at the 5 minutes resolution. And so in the very limited setting of Brownian models, we know that there is always the same relationship basically between the two time series up to a scaling factor if their increments are correlated. Okay, so if you use these very simple models, if your say 1 second increments are correlated, you will find the same kind of correlation with a certain scale factor at 1 minute or 5 minutes, and so on and so forth. The reality of signals, though, is quite different. And in co-integration, we see that we have a certain equilibrium between two time series that is only true at very long time scales, but really not there when we take a look at what happens at a second resolution, for example. And so to be able to not have a prior when we take a look at these different correlations across scales. So one of the great things about that is that, well, if there is no relationship at a small time scale, we'll still be able to detect the relationship at the longer time scale. Okay, so that's a very powerful tool to analyze what's going on stock markets, for example, or in econometrics in general. And so one nice thing about wavelet transforms is that, as opposed to the dyadic decomposition, now we can formulate a representation of signals that is no longer redundant. So we managed to project our signal on an orthonormal basis, which means that each of the coefficients of the projection on this basis is giving an element of information that is really increasing what you know about your signal with respect to all the other coefficients. Okay. So in other words, in an orthonormal basis, if you were to zero out one of the decomposition coefficients, you're sure that you're going to lose information because there is no redundancy. The reverse of that is that if you compute something, you know it's useful. You know it's going to improve how much information you have in your signal. So to a certain extent, having this orthonormal transform, is a way of making sure that you're computing efficiently. You're computing a meaningful and efficient representation of your signal. The good news for us is that in the setting of dyadic decompositions, so when we choose dyadic scales, we have a fast wavelet transform algorithm that really makes computing such a decomposition very cheap on in the discrete time setting. And so typically, if we have a time series of length t, we'll see that we'll have an algorithm that will decompose the time series on a wavelet basis in O of t operations. So it's really great, it's really fast, and everything would be basically would have solved the problem of this representation of signals. As soon as, given this wavelet transformation, we also have some guarantees about how well it approximates certain classes of functions. The thing is that if you want such a guarantee to be available, you need to choose your wavelet basis. And we'll see that we have two knobs when we choose a wavelet basis to characterize, to basically to be able to tailor it to a certain class of functions that are related, in fact. So when you design a wavelet basis, you'll in fact have a trade-off that may be hard to decide from an analytical standpoint. Fortunately, today, we don't really need to do that beforehand. We can let the data speak for itself and let the wavelet basis be decided by, say, SGD as we train the basis to reproduce a certain class of functions. Okay. So I'll talk about that. And finally, I'll show you how we can, after this exploration on the theoretical side of the very nature of continuous time signals, how we can go back to deep learning and very recent improvements that have been shown in the field of multiscale interpretation of scenes or also speech synthesis. So just to go back to wavelet functions. So the basic idea here is that instead of decomposing a signal across as a sum of oscillating functions, we choose to decompose it as a sum of local averages and local differences. Excuse me. And so the key aspect in the dyadic setting is that at each scale, basically each time we go to a coarser scale, we take whatever the basis for the decomposition we had, and we dilate it by a factor of 2. So the reason why we were doing that is in fact related to this Heisenberg uncertainty principle. So if you remember the representation of the windowed Fourier transform in the time and frequency domain, you had a theorem that told you that each atom of this representation of the time series has to have a non-zero area. And so therefore, in the case of the windowed Fourier transform, because your spacing in the frequency domain is constant, because your spacing here in the time domain is constant, you have a constant spacing in the frequency domain. That's not really great, basically. To have the very same atoms at the low frequency and the high frequency is not ideal because typically events that correspond to high frequencies in a signal correspond to abrupt changes that are better characterized on short time scales. So that's what this principle told us at the very beginning of these lectures on Fourier decomposition and wavelet decomposition. We may want to play around with one of these factors to be able to take these ellipsoids here and, for example, shrink them in the frequency domain, which will elongate them in the time domain, or shrink them in time, which will elongate them in the frequency domain. That means that we want to have a picture that looks like that. Okay? What is cool about this representation is that now, as I have a form of adaptive resolution in the time domain, I also, so there is a cost to that. If I want to have shorter time domain pixels, I'll have an elongation in the frequency domain. Here it's not a big deal because I make sure that these short-term variations are mapped onto high-frequency components, which really works well. I mean, these sudden changes will be very well accounted for elements of a decomposition that correspond to the high part of the spectrum. So that's a picture that's radically different. Now I have also a lot of time to characterize phenomena that occur at a low frequency, which is also really what I want. It will make them much more easy to detect and account for accurately. And incidentally, when we have a dyadic decomposition, that's exactly what we do. Okay, here, for each scale of the decomposition, I reduce the scale of my pixel by a factor of 2, and as a consequence, the stretch in the frequency domain of each of these atoms is also multiplied by a factor of 2. Okay, so that's one of the objectives we had with this dyadic decomposition. One of the motivations we had. Now we have a much better adaptation to signals that can have sharp changes in time and also need some frequency domain localization. Speech is a very good example of that. There are abrupt changes as I speak. silences, high-frequency components, and if you want to understand my tone at the same time, you'll need to be able to map this information in the frequency domain. Okay, so we need both time and frequency domain localization with that particular shape here, where basically we want to capture high frequencies on short windows of time, which makes more sense. Okay, so just to give you a practical idea of the implications of this certain lattice in the time frequency diagram, I'm going to take an input here. So it's a certain time series. It's basically it's a modified version of the airline passenger time series. And so it's something that's fairly hard to approximate in the Fourier domain, because although I have these periodic components here, you can see that I have also very sharp and abrupt changes in this time series. It's also non-stationary. I cannot really find any periodicity here other than these 3 spikes. Okay, so it's something that typically a Fourier basis will struggle to represent, in particular because it will spend a lot of coefficients trying to account for these sharp edges here. Okay, so let's employ this cascading algorithm that I showed in the previous lecture, where I take my signal and for a given scale I pass it into 2 filters. A high frequency filter, so the scale filter, and a low frequency filter, so the scale filter, and a high frequency filter, the wavelet filter. And so here at each scale, basically, I'll take my input signal and I'll decompose it into its local averages here at a certain characteristic time scale and its local differences. Okay? So I can do that. So now I will take this scale and I will do the very same thing. I will apply a high frequency filter and low frequency filter. You can see that now I get a signal that's even more smooth, and I get details that are a bit coarser, okay? And so on and so forth. So each time I take the resulting scale signal and I apply these 2 filters that will separate out the frequency domain into 2 separate subspaces. And finally, that's what I have at the coarser scale. Now you can see that I only have really the broadest stroke of this time series. So to a certain extent here I've denoised it. But I've kept some information about what happens in terms of variations. So now I can do, yeah.
Why the vertical axis keeps increasing?
Yeah, so actually, that's a very good question. You may want to have a scaling component here, so a scaling factor, if you don't want to increase the size of so this value here. We'll see that when I have a wavelet decomposition, it's not really a problem, and in fact, it's how I can keep the same amount of energy in my decomposition that I have in my input signal. Okay, so this is only a problem here because as I have redundant information, I will basically have a representation that will have a higher amount of energy than the input signal. So that's one of the limitations of the dyadic transform. You'll see that once I have introduced the wavelet transform, this is actually one of the things I want if I want to preserve energy. So just keep that in mind, and I'll come back to it. So here, just to illustrate what's going on, so I took my input, and I separated it out into 2 signals. So that's my g of t. And here, so I have my low frequency decomposition, basically, at the first scale. So that's where I get these this first decomposition, and then I have the details, so the high frequency components at the first scale. So that is this picture here. So then what I do is I take this low frequency filtered signal and I apply the very same filters with a certain dilation factor, so that now I separate it out again into its low frequency component, but at a coarser scale now, and a high frequency component. The good news is that with the way I've chosen my different filters, the information that I have here will basically not overlap that much with the information I have in the first high-frequency filter. And so to a certain extent, you can think of this decomposition. So that will actually be true in the wavelet decomposition as something that takes the energy of your signal and separates the energy out into a dyadic tree. So what I do here is that, so I apply these two filters. So that's low frequency one of G and high frequency one of G. So my here I have my scale filter at the first scale and my wavelet filter at the first scale. So here I have no dilation. Then I take this signal now and I dilate my filters, which basically also shrinks the bandwidth of each of the high frequency and low frequency filters. So now I can take basically this subspace here and start dividing it out into two subcomponents. So one of low frequency and another one of high frequency, and so on and so forth. So I keep decomposing my space like that with those cascading filters. So to give you another way of representing that, I'll apply the convolution filter S and the convolution filter W here at the first scale. So I keep this information in mind, and then I will only operate on the first output of the scale decomposition. So this is this function here that I obtain as a result of this convolution. And then I keep applying these filters, but with a certain dilation factor. So you can think of it as just a dilated version of kappa of omega and kappa of W and kappa of S. Okay, so I keep basically separating out my input signal into elements that will capture coarser variations, elements that have the finest level of details, and then coarser level of details. Okay, and the cool thing is that if I keep in mind, say that I do it one more time here. So here I have a decomposition, dilation, sorry, with a factor of 2. Here I have a dilation with a factor of 4. So what I do when I take a look at this, I cannot use colors. So when I take a look at this decomposition, what I remember basically are just the wavelet, the wave component, so the different level of details across scales, and the last low frequency decomposition of F. So what I will remember here is this first wave component, the second wave component, third wave component, and then this last wave component, and finally the last scale I get. And that's all I need to remember. I can forget the intermediate scale components at the intermediate scales. Okay. Now, what's kind of great with this decomposition and elegant, sorry, what's going on? Oh, yeah, let me do, is that working? Okay, so now what is kind of nice and elegant about this decomposition is that I can take each of these elements and start recombining them following the very reverse of these convolution filters. I mean, I will have to play around with how I pad with zeros and also with my dilation factors here. I will have to reverse some of the filters, but basically the parameters involved are the very same. Okay, there are just some reversions of the filters that are occurring here. So I can take these two components and then reconstruct the latest, I mean the scale decomposition that was one before last. Then I take these two components and I can reconstruct this second scale decomposition, which looks like this in practice. So I take my coarsest level of scale decomposition and I recombine it with the details of this level. I get a refinement of my process now. Okay, I'm starting to incorporate the high frequency details as I go up in the tree now. So yeah, I'm applying filters that are, for example, reversed, so they are not exactly identical, but they involve the very same parameters. They are just the transpose filters, basically, okay, which makes all the code for this very easy to write. So what's interesting about the dyadic decomposition is that I take the broad strokes of my time series and I start refining them with the high-frequency components that I've remembered about each characteristic scale. And as I do that, I end up with a signal that is the very signal that I started this decomposition with, which means that I'm able to reconstruct my signal with the information I had. The only problem here is that there is a certain level of redundancy in the information I kept. So from a compression standpoint, I could do better. That's what we are trying to do today. But here I have achieved this aim of having a certain representation at different characteristic scales that has lost no information about my input signal, which is already fairly interesting. Also, what's kind of cool about this decomposition is that the number of dyadic scales you have for a signal of length t is, so you have log t, O of log t scales. Okay, I mean, in fact, you'll have log t in the base 2 scales involved, which means that overall the complexity of the algorithm for decomposition will be log 2t t, I mean with a certain constant in front of it, and the reconstruction will be exactly the same complexity. Now the caveat though is that for a certain reason here, because there is some redundancy in the information, what I need to keep in memory is also t log 2 t, okay? Because I keep a very high resolution even at when I try to describe these low, these very smooth components. So that's why there is a bit of redundancy here, okay? I don't need that level of resolution if I want to characterize a function that has a certain band-limited spectrum. So I can do better in terms of how small a memory I need to represent my signal across scales. And that's the point of the orthonormal wavelet decomposition. So the orthonormal wavelet decomposition is great when we really try to achieve, you know, a very small, a very good compression, when we try to memorize a signal as efficiently as we can. But it has its shortcomings. And in particular, one of the things it's not great at doing is unraveling some properties of processes that are only revealed across scales and that need some level of translation, some robustness to changes in translation. So one of these properties is called cointegration. We'll come back to it when we study long memory processes. Cointegration between two processes means roughly that you have two processes, each of them is not second-order stationary, for instance. So you'll have, say, a Brownian motion, like this. You'll have another Brownian motion. And here, for instance, if you're trying to apply a strategy that bets on the mean reversion of these processes, this is not going to work because these processes, in terms of how far they can go from zero, is absolutely not controlled. Okay, if they are Brownians, for instance, they can go arbitrarily far from zero. So cointegration is a definition of the following phenomenon. There exists certain constant a, such that a linear combination of x and y of t, and maybe I also have a certain affine coefficient here, like c, to absorb the difference in averages, becomes, so this linear combination becomes mean reverting. So we can have a bit more narrow definition and say that we want, in fact, second-order stationarity for this process. Now, the reason why it's of such a big interest in trading is that now if you want to apply a mean reverting strategy on this process, you know that with a finite expectation, I mean, you know that the time you need to revert back to zero has a finite expectation, for example. Okay? So that's the basis, for example, for saying that when this process is above zero, this portfolio is overvaluated, so you should short it. And when it's below zero, it's undervaluated, so you should long it. Okay, and then you can start making money. This kind of relationship is important not only in the field of arbitrage, statistical arbitrage, which we have here. It's also important in macroeconomics when we try to say that we have two stochastic processes that to a certain extent are related in the long run by an equilibrium relationship. And so typically this equilibrium is described as this linear relationship. So one nice thing about cointegration is that it's really a definition that is not redundant with other features of the time series of interest, such as the correlation of their increments. So as an experiment, you can take two second-order stationary processes and have a level of correlation that's like 0.99999. Okay, so you create two such processes of variations, delta x and delta y, very high level of correlation, and then you compute the cumulative sum of delta x and delta y, so that now you get x and y. Okay, so you have two Brownian motions with very highly correlated increments. Well, you still don't get processes that are cointegrated. In fact, what will happen is that you'll still have some amount of residual noise at each time step that will affect one of the processes but not the other, for example, in an orthonormal manner. So that means that in the long run, these two highly correlated Brownian motions will drift apart. And in the long run, this short-term relationship between x and y about their first-order differences will not lead to a long-term equilibrium. Okay? Yeah?
Would it be possible to give an example of this?
Yeah, I'm going to show you that. Yeah, I know it's a bit difficult to grasp it with that theoretical definition. So I thought it would be best to show you an example. So here you have two time series. So it's Cisco and Intel Corp. I took 1 month of these two time series, and that's the price in intraday. And you can see that, so for example, here and here, I have a slightly different behavior. So the time series on the right is hit by a temporary deviation that does not affect the time series on the left. But if I take a look at in the long run, I will have a correction that will make them look, after a certain normalization, extremely similar. Okay? And you could test this time series and find out that, for example, they are cointegrated or fractionally cointegrated, which is fairly similar. So as you can see here, at the fine time scale, I have a lot of noise. I don't have the two time series do not look very much alike. I need to zoom out, basically, to find out that the long-run variations of one are very similar to the long-run variations of another, which means that I could find the coefficients A, B, and C such that this relationship is true. Okay. What's kind of nice is now to take a look at this time series through the dyadic decomposition lens. So here I chose a certain wavelet function. Excuse me. So I think it's, if I remember correctly, I chose the Mexican hat function. And here you can see a decomposition across scales. So the scales go from fine to coarse, from the top to the bottom. And what I represent here in red are so high magnitude wavelet coefficients and high wavelet coefficients, and in blue low wavelet coefficients. Okay. So what I can do is take each of the decompositions here and then compute a correlation, for example. Okay. So now at each point in time, I can compute the covariation, in fact, of the wavelet coefficient. So I'll take this pixel here, this pixel there, and I'll multiply them out. Okay, that gives me the equivalent of a covariation, but this time in the wavelet domain. To a certain extent, these coefficients here for the wavelets, they correspond to short-term, variations over a certain characteristic scale. So what I can do is the very same thing that I used to do with delta x and delta y. I can try to compute this quantity, okay, map it through time, and then if I want to get an aggregate, I could sum it up. Okay. So here what's nice is that I'll compute this quantity for t on my time interval, but also across scales. Okay. And S here will be, in fact, a dyadic factor, so a scale that's a certain power of 2. So I can compute these elementary multiplications, and I get these different mappings that will tell me basically when the variations of x and y went in the same direction, positively, for example, which is the case of this coefficient here, and when the variations went negatively in the same direction. What is nice is that you can see that at the short time scale, they seem to there doesn't seem to be a lot of consistency between the variations. Sorry, I think actually, sorry, that's x against x, so that's delta x here. On the right, it's delta y, and here I have delta x, delta y, so the cross variation. So now I can take each of these series of covariation across time for a certain scale, and I can compute an average for this quantity, okay, which gives me an estimate of the covariance at a characteristic scale. And what I see here is that at long time scales, I have a lot of correlation here once I have normalized this covariance, but it's much smaller at smaller time scales, okay, which just correspond to this intuition, to this intuitive definition of the cointegration as, well, in the short term, there's not really a strong relationship between the two time series, but in the long run, they are extremely related one to another, okay? As I plot the correlation of variation across scales, I can see that as the scale goes coarser, my correlation increases.
Sorry.
Yeah.
Like, I'm really confused as to what the patterns are now.
Yeah.
And what the y-axis and x-axis in each of them.
Sorry, let me explain that again.
Scale same, because I can't read.
Yeah. So here I compute the dyadic decomposition of the time series on the left, which gives me that 2D map, okay? And I compute the very same decomposition for the time series on the right. So in 2 dimensions here, I should have a label for this axis. So the horizontal axis is time and the vertical axis is scale. And then I have a certain level which is given by the heat map here. Okay? So it's the magnitude of something that looks like a differentiation of your time series. Only it's not first order differentiation. It's a higher order, but I mean, you don't really care about that. Okay? It's an atom, basically, of decomposition.
And how is this continuous along the y-axis?
It's not continuous. It's just so to make the plot look more beautiful, you interpolate it, which is what matplotlib does. Otherwise, it's very hard to read. But I'll show you an instance where you don't have this continuity, if you want. It's just much harder to read, basically. Okay. If I was not choosing an interpolation here of the plot, I would not have this continuity. That's a very good question. Sorry, I should have mentioned that. So I get the decomposition of these time series as atoms at different times and across different scales. Yep.
I think the y-axis is time, right?
No, it's actually here, for example, you can see this bump.
0 to 330, right? And it's the same as the first 2 panels.
So oh no, that's just the pixels. It's because when you do imshow with matplotlib, you get that silly axis. Yeah. So it was hard to render these plots really well. I still need to better master matplotlib, I guess. But so on the vertical axis, it's the scale from fine to coarse. Top is finest, bottom is coarsest. And then I still plot the time axis horizontally, as I did for the time series. So now I roughly speaking decompose my time series as characteristic atoms that correspond to a certain level of variation. So here, in fact, it's second order variations. It's like the second order derivative. And you can see that it makes some bumps very salient at some scales, like these things here. So now, as I have a different representation of my time series, this time in 2D, but I mean, it's still a representation, I can, for example, compute elementary product of the 2 images that I have here. So pixel to pixel, I can compute an element-wise product, which is what I have represented here. Okay? So if you were to sum this, each of these rows across time, you would get the amount of variance, for example, of this time series at a characteristic scale. Same thing for y. So these are the variances. So they are the variations of x against the variations of x. On the right, I have the variations of y against the variations of y. And then I can compute a cross variation, so covariation of x and y, which looks like this. Okay? So now I have this decomposition across scale and across time. I can collapse the time dimension and compute a characteristic correlation at each scale, which looks like that.
Sorry, I'm still not clear on what the second row is.
Which one? This one?
The third row.
Third row? So the third row, sorry. So, all right. So I have my time series. So here I have x of t and y of t. Here I represent so the wavelet transform with respect to a certain w of x at t and a certain scale 2 to the power of L. So L goes like this and t goes like this. Okay? Same thing here. Then, so this is an image, okay? It's a 2D matrix. What I can do is compute the magnitude squared, if I want, of each of these elements. Okay? It's as if I was squaring all the different pixels of an image. Okay? Gives me basically the repartition of energy across scales and across time of the variations here of my function. So same thing here for y. So these are this reveals information that is intrinsic to each of the time series. Okay. Now, if I want to understand the relationship between x and y, one thing that I can do is what I have in that very last, plot. I can now compute wt, so the wavelet transform of w with respect to w of x at t at the scale 2 to the power of L times the same thing for y. Okay? And then I can take each of these rows. I can sum, all right? I normalize by these two sums as well on the rows in square magnitude. Okay, one for x basically, and one for y, which then reduces the covariance here of the wavelet transform to a correlation. And now for each scale, I can plot a certain correlation of these characteristics or variations, and examine at which scale I have the highest amount of correlation between those atoms that represent my time series. Okay? Does that make sense? Sorry, I should have probably started with that. I should have added a slide.
Nonetheless, this is
Yeah.
about the colors and just the plotting. How does the light blue, when squared, becomes dark blue? Why is it going down? Is there like less than one somewhere?
Sorry, at which level? Here?
Going from the second row to the third row at the top, the light blue becomes dark blue. Why is that happening?
So the light blue here, as you can see, the light blue is has a magnitude that's close to 0.
Oh,
Okay? So when I square it, will look very dark because it's close to 0. Okay? So then I can take a look at another day and conduct the very same decomposition across scales and the very same correlation. And now you can see that here I had a lot of variations at small scales that were not matching for the two time series. Okay? However, in the long run, they look very similar. So I still see a degradation of the amount of correlation I have at the small time scales, which reflects the fact that here you can see that this one jumps up and down when this other time series has a downward trend. So they don't match really well at this certain scale. But then if I really take a look at the coarsest scale, well, I have a high amount of correlation. And I can do the same for different days. Okay, I can see that steadily, although in the short run I may have two time series that do not behave similarly, in the long run, they have the same kind of behavior. Which gives me also, yeah.
So from a trading strategy point of view, does that then just imply that for these to be mean reverting, or if you wanted like to buy one short the other one, you would have to wait a long time for your strategy to pan out?
Exactly. And that, which is a plus, gives you the characteristic scale at which you can expect these reversions to occur. I mean, okay. So at least that gives you roughly the time interval that would be the unit interval for these mean reverting components, for these mean reversions to occur. you have another aspect that will decide on the expected time you have for mean reversion, which corresponds basically to the amount of correlation you have. To the amount of it's actually the amount of anti-correlation you have in your residual. So if I come back to this definition here, I have this epsilon, which is my mean reverting process. If epsilon has a high amount of autocorrelation, it will have huge swings and will take a lot of time to come back to zero. If it's a highly anti-correlated process, it will oscillate very often, and so we'll have a lot more zero crossings. Incidentally, you can take a look at a lot of these strategies, for example, and find out that this autocorrelation coefficient is a good predictor of the performance of a strategy. Okay? The problem is that this benchmark does not tell you at which characteristic timescale you should compute this linear combination, and at which timescale you should compute the autocorrelation of epsilon, so the residual process. This is answered by the decomposition in co-integration, which you get here. What you can do then is take a look at another process. And so here, I could do the very same kind of comparison, decompose Procter and Gamble and Pfizer across times and scale, and see that, for example, here I have a characteristic scale where the correlation between the behavior of PG and P was really lower. And here I can see an example of a day when I did not have co-integration. So you can see that here, this behavior here in the long run looks very different from the time series on the right from what happens from the time series on the left. They, even if you normalize the prices to 1 at the beginning of the day, here at the end of the day, they would end up being radically different. And it's probably because fundamentally the prices of these companies do not have the same kind of relationship as the relationship that Cisco and Intel Corp share. Okay. Here you can see another day that looks a bit more co-integrated, and again, you have a higher level of correlation at the coarser time scale, which gives you basically a way to diagnose what happens between processes without having to specialize on a certain scale. Now you can decide a posteriori at which scale the relationships of interest are actually occurring. Okay?
Does this give us a way to find the coefficient A?
It could, I guess, but really the way of finding A is just to conduct a linear regression of one time series onto the other. So we'll see next week that if you conduct that kind of linear regression on two Brownian motions, so long-range dependent time series, all bets are more or less off in terms of the convergence of the coefficients you find, unless the time series are co-integrated. In which case you find that the coefficients of the least square regression converge extremely quickly to the actual coefficients in the theoretical relationship you have. And that started basically the whole study we find now in the field of long memory processes. So we went from a disastrous estimation procedure to actually the characterization to a new class of phenomena, co-integration in this case. And so if you're curious about that, you can take a look at the papers by Granger. In '69, he wrote a paper about co-integration and these spurious regressions. So what are we doing exactly with these multi-resolution decompositions? So we are basically building a certain set of desiderata, as I said last week, and we want typically to have decompositions that are increasing in scale and decreasing in the amount of information they can entail. Okay, and typically, if I take the decomposition at a coarser scale, I will be able to express it with the decomposition at the next finer scale, and therefore at the decompositions at the scales that are finer in general. So that's my that's what I call a multi-resolution decomposition with a dilation factor of 2 here. And we saw that to characterize such subspaces of L2 of R, we wanted also a scaling function that was giving us an orthonormal basis for the different subspaces. And we wanted this orthonormal basis to be obtained by just dilations and translations of the elementary atom S here that we use to characterize our functions. So that's just a reminder of the kind of necessary conditions we had on this fundamental pixel function and how they could be easily expressed in the Fourier domain. So if you have this first condition, which is complementary to that other mirroring condition in the Fourier domain, you knew that you had a scaling function that you could use for the dyadic decomposition, provided you were giving it a mirroring detail filter, okay? That I obtained in the Fourier domain thanks to this operation, okay? So that's how I obtain the decompositions. I know that with this decomposition, I can recompose my signal as long as such a mirroring condition holds between the scaling filter and the wavelet filter. And so as soon as basically these conditions hold, I know that I'm able to build up a dyadic decomposition. The problem is that it's not enough because, as your classmate mentioned, there is a problem with the characteristic scale of this function, and basically we'll end up having an energy in our decomposition that is higher than that of the input signal, which means that, well, we don't have yet an orthonormal transform on our space of interest. And so the way we can end up having this orthonormal transform on an actual orthonormal basis for decomposition is by saying that I can take any subspace of the dyadic decomposition at level L+1, so at a coarser scale than L, and I'll decompose it into, sorry, that's H of L here. I'll decompose it into the space of finer scale, so H of L, plus an orthogonal complement. And here you see the very same pattern as in this decomposition. Here, for example, this coarser level of depiction of my time series was obtained, could be recombined. Sorry, when I recombine things here, you see that for each coarse description, to recompose my input signal, I need also a finer level of description, which corresponds to the effective detail of my function. So I separate out each scale space into a component that is the finer scale space and also an orthogonal complement, which I'll call the detail space. Now, if I find an orthonormal basis for H of L and an orthonormal basis for D of L, I have found effectively an orthonormal basis for H of L+1, and provided I have some properties on D of L and H of L, I'll be able to find now an orthonormal basis for the entire set of scales and decomposition times, which is what I do here. And so there is a theorem that's a bit hard to read. I just wanted to present it here holistically for the sake of accuracy. But basically, you apply a certain, you ask a certain set of conditions to a scaling function. You create a wavelet function through its wavelet filter with that condition, basically, which in fact you can reduce to something like that. Then if you have this and this condition, you get the mirroring between the wavelet filter and the scaling filter, which tells you that you'll be able to recompose your signal. What is great is that if you choose this particular scheme, now you'll find with the wavelet basis, now not the scale basis, an orthonormal basis of the detail space, D of L, for example. Which means that in fact, if I recompose now L2 as the sum, as the orthogonal sum of these different detail spaces, if I have found an orthonormal basis for each of the subspaces, and I combine the different bases, now I have an orthonormal basis for my entire set of L2 of R, okay? Which leads to this theorem, basically. Now, with the wavelet decomposition, I have effectively found a non-redundant expression for any function with a finite energy. Okay, this theorem is pretty hard to prove. I have a short proof in the lecture note. What is important is the conclusion and the generalization we get here. We knew that this result was true for Haar functions. And that's a fairly old result from the beginning of the century. The question here was under which conditions on my atoms, so my scaling function and my wavelet function, I could generalize this result to a broad set of atoms in my decomposition. So one thing that was a bit hard to parse in the conditions I had was this mirroring condition, which is expressed primarily in the Fourier domain and may seem a bit hard to enforce. What happens is that, in fact, if I have this relationship between my wavelet filter and my scaling filter, I get the mirroring condition, And I mean, I also get, sorry, this condition here, incidentally. So as soon as I have a wavelet filter that is expressed as follows, where kappa of S is a scaling filter, a valid scaling filter, I have found a way to decompose my space of interest into orthonormal components, which means that the orthonormal basis comes as a cheap byproduct of the hard part, which was really finding so a set of orthonormal bases for each scale of the dyadic decomposition. As soon as I had that, which was really hard to devise, as soon as I have the proper characteristic for kappa of S, I can find kappa of W very quickly. And here you can see a funny relationship between kappa of S and kappa of W. If I take for example, a Haar function, and I plot the corresponding scaling filter. So it's going to be this discrete time function, okay? It takes in -1, sorry, well, in 0 it's 1, and in 1 it's 1. If I try to find the corresponding wavelet filter, so typically I'll conserve, it depends on, so the first component will not be changed, and then the next one will be flipped. So its sign will be changed because of the -1 to the power of 1 minus t here. Okay? And so what that means from a very high level is that I effectively have a function that computes these local averages, and then its counterpart is here to account for local differences, and it's the local differences that give me those details that enable me to progressively refine a certain decomposition. Okay? And that's, I think, from really a high level of understanding of this decomposition, much easier to grasp as a human, refining these details, than adding trigonometric polynomials and eventually finding a function that looks like our input, at least personally. So now, the cool thing about this decomposition is that it's also cheap to compute with convolutions. And when in the dyadic decomposition setting we had dilations, here we have strides. Okay? So instead of dilating our filter, we just compute one output every 2 iterations of the convolution, or every 4 iterations, and so on and so forth. So basically, I just zero out some of the outputs of the convolutions and forget about them, and I obtain a characterization of my input signal, which is sufficient to reconstruct it, and also orthonormal, so not redundant. And the pattern here is very simple. Basically, I just, for a given level of decomposition at the scale L+1, I take whatever I had computed previously at the next finer scale. I apply the scaling filter with a certain stride, 2 to the power of L. I apply the wavelet filter with the same kind of stride, and I get progressively a wavelet decomposition. And you can see that here at each scale, I will have a lower number of pixels in my representation. So if I have 8 pixels in my input signal, the decomposition at scale 1 will have 4 pixels, and then I will divide the number of pixels by 2 again, and so on and so forth. So that's the influence of the stride here, as opposed to the dilation. One key element of this is that if you have strided outputs, if you offset, if you jitter your input in time, you could have radically different coefficients at the higher scale of your decomposition, which may be ill-suited for some analysis, such as the multiscale analysis of cointegration that I gave you. With that analysis, I would like the coarser decomposition to be fairly invariant to shifts, short shifts in time of the input signal. If the coefficients change radically, it's not exactly comfortable for me to analyze what's going on. And in terms of recomposition, well, I do very much the same thing that I used to do with the dyadic decomposition setting. I take transpose filters, and I just recombine their output, and I'm able to progressively refine the representation of the signal I have. So what that means in practice is that I take my input, and now each time I produce the next level, yeah? Yeah, so, well, let me show you this with this example, okay? So here, just keep in mind that I plotted this time series with a line, so implicitly there's an interpolation here, but effectively each of these decompositions are just vectors, right? So sets of discrete points. And here you notice that as I do the first level of decomposition of my input with the wavelet decomposition, I divide my resolution effectively by 2. And I keep doing that. So then the next level, as you can see, has much fewer elements to represent it, and so on and so forth. And so what could happen here is that, for example, if I was to jitter this output a bit, so translate it, say, by 1 shift in the time domain, this coefficient, for example, here, could move to the 4th coefficient.
During, like, between scale 3 and scale 4, or at the beginning?
No, at the higher scales generally is when it happens. Because you have basically a very few pixels to represent time. And so what can happen is that short shifts in time, if they're at, say, a boundary, will completely move a coefficient out to the next time step. Okay. So what's great is that here I leverage the fact that this representation is extremely smooth and typically has a short bend in the frequency domain, so that I know that I can represent this function with a very sparse sampling in time, which is what gives this minimality to this decomposition, basically. It's important that I use fewer pixels at each scale to avoid redundancy, basically. And same as before, I can progressively take a very coarse reconstruction of my signal and refine it with the details. And in the end, I get the very same input. Okay? And you can check with NumPy, for example, as you do this decomposition, that if you take the square of this wave, the square of this wave, the square of this one, and the square of these two guys, you find exactly the same value as the square of this input time series. I mean, up to an epsilon because of the numerical errors, but that's something that's that can be very quickly checked just to verify that effectively your decomposition is orthonormal, and one of the requirements for that is that it preserves energy. Okay?
This was not the case in the diadetic.
No, it was not. You could actually effectively compute the square, and it's just that, well, you can easily imagine that if I get the same amount of energy with the squares of these time series, which are effectively very short because they have few timestamps, if I take the same dyadic decomposition with redundant pixels, I will obtain a much higher level if I compute the sum of squares. Okay? So there are pros and cons, basically, for each representation. It depends on whether you're aiming for compression, for instance, or featureization to highlight some important elements from a statistical standpoint of your input. And also, because of the stride, now at each scale, we compute twice as few convolutions, okay? Which means that effectively now the complexity of the algorithm is O of t. Okay? I eliminated, basically, the fact that for each of the log2 scales, I needed a convolution of a sequence of length t. Now I convolve with a sequence of length t over 2 to the power of L. And so if you sum that, you find t. Okay. So it's kind of cool. It's faster than the fast Fourier transform algorithm, by the way, which is why it can be interesting if you have a crazy latency sensitive, if you're operating in a very latency sensitive setting. And the last thing I wanted to bring up is how to choose your wavelet basis. So here we find a way to represent signals of L2. We can prove that, so not only do we have the orthonormality of the basis, we also have a certain density in L2 of R, which means that, okay, in theory, if we have an infinite number of coefficients, we can find a discrete infinite sum of functions that can recompose any signal in L2 of R. And from a mathematical standpoint, at least in theory, we've kind of won. I mean, it's very interesting to be able to have this vision over these square integrable signals. To a certain extent, now we understand better what they are compound of. The thing is that if we really want to compute over these representations, we can't afford to have an infinite number of coefficients, and so we probably need to cut off the approximation. So there are various ways of finding these approximations. There's been a large study, in particular in the field of compression, to determine how, with as few wavelet coefficients as possible, I can effectively recompose an image accurately. And one of the elements that are involved that will decide on the effectiveness of your approximation are the number of vanishing moments that, in fact, it's a wavelet function or the scale function. I mean, you can compute this for each of the, for any function g actually. So a vanishing moment, sorry, that should be g of s. So a function is said to have a vanishing moment if its moment of order k for any k below p is 0. Okay? This has a strong implication. It means that this function, so if s was to verify that, s being the scaling function, it would mean that it's orthogonal in the Hilbert space L2 of R to any polynomial that has a degree less than p. Okay? It means that if you take a certain class of function now, you have atoms that are completely orthogonal to it. Now, if you take a look at the Taylor decomposition, for example, of a certain function, you can express f as a certain polynomial of degree p plus a residual, okay? And the magnitude will depend on the behavior of the derivative, say, of order p plus 1. So now you see that if you project that onto the basis, all the polynomial coefficients will zero out, and you'll just get the residual of the Taylor expansion projected onto the basis as a magnitude of the decomposition. So that's one element that can explain how you can, with very few coefficients, express a function accurately. More generally, you have a theory of multi-resolution approximation error, which was mostly developed by Mella, that tells you that if your function W has vanishing moments and other properties that make it more or less well-behaved, for any function that is so smooth, so here, if f, actually it's 2 to the power of s here, so basically if g is in what's called a Sobolev space of order s, which basically gives you a set of functions that have a typical decay in the frequency domain in their Fourier transform, and therefore a certain level of smoothness, well, these functions have a certain bound on the value of the coefficients of their decomposition. And so here, based on this bound, you can quickly derive the speed at which the coefficients of the wavelet transform vanish as you go across scales, typically. Okay? And so you need a certain class of functions to be able to characterize this property. So you require some properties of the Fourier transform of f, a certain degree of limited band. But if you have that, now depending on the properties of vanishing moment of your choice of the wavelet function, you know that you'll converge more or less quickly towards the exact value of the function with a finite amount of coefficients in the wavelet domain. And so, yeah.
I'm not sure what you mean by coefficients of the wavelet function, because at each step you have the time series things.
So it's these guys. Okay? The wavelet basis is orthonormal. So if you project a function onto the wavelet basis, the coefficient is determined by these by these inner products, right?
For time series of length t, you basically have finite decomposition of that, right? At each step you have like.
Oh no! Here I'm talking about elements in L2 of R.
Oh, like an entire.
Yeah.
Time series.
Which is why I need also the condition, the Sobolev space condition, basically a certain degree of smoothness. Otherwise, I mean, if I had arbitrarily complex objects, it would be somewhat interesting that I would be able to approximate them very well with a certain number of coefficients. You know, so here I ask that my objects are not completely arbitrary. Okay, and it's the kind of band-limited conditions you find as well in the representer theorem in machine learning. Okay, you know that you can represent your optimal function as a function of the data if its Fourier transform vanishes fast at infinity. Okay, so we kind of find always the same kind of conditions on the class of function that we are working with to enable an accurate decomposition with a finite number of representers. Okay, so here, one of the things we may want to do for certain classes of functions is to have a number of vanishing moments for our wavelet function that is as high as possible, say, okay? You're studying a certain class of functions, and so you want as many of these moments as you can. But the thing is that for the wavelet decomposition to be interesting for you as well, you would like to localize the decomposition in time, which means that each of the wavelet filters or each of the wavelet functions, you would like to have for them a compact support. If the support is not compact, you're back with the issue you had with Fourier transforms. Each of the atoms in the Fourier domain has an infinite support, and therefore any perturbation to your signal at any time will affect all the coefficients. What we would like in the wavelet decomposition is that if there is a perturbation, it only affects coefficients that are somewhat close in time to the moment when this perturbation was happening. And one practical representation of that is, if you remember this video and this moment when I was driving and I drove over a set of over a railroad track. Here there is a shock, and what is nice is that the impact in the wavelet decomposition is somewhat contained. Okay, that's a consequence of having a wavelet with a compact support. If the wavelet had an infinite support, this perturbation here would leak across all the different time steps, and I really don't want that. So here I would also like, on top of the of my wanting vanishing moments, I would also like my wavelet to have a compact support, and preferably a support as small as possible, so that when I have localized features of my time series in time, they're also captured in localized manner in the wavelet domain. And there is a theorem that was discovered by Dobeshiz, who created the family of wavelet functions with the same name, that tells you that you cannot have an arbitrarily small support for your wavelet function if you want a certain number of vanishing moments. And the functions that give you this optimality are what was called by the Dobeshiz wavelet. So Dobeshiz, she found out that this theorem was true. So there is a trade-off inherently between the number of vanishing moments a wavelet function can have and the compactness of its support. The more vanishing moments you have, the broader the compactness, the broader the support. And she also found out when she was working at the Bell laboratory that you have a family that achieves this form of minimality. So you have a family of wavelets that has the number of moments, number of vanishing moments we need, and also has the minimal support size. And these are called the Dobeshiz wavelet. So the thing is that in practice, solving this trade-off may, so this is a general statement about a basis of L2 of R. The thing is that when you're doing, when you're working with a set of signals, it's probably not the full set of functions in L2 of R. It's probably a functional, a sub-functional space, okay? And that means that perhaps now you would want to find a wavelet function that is very well tailored to the very signals you're working with. And for this, that's where, for example, optimization with deep learning can come in handy. Now you can say, I want to have a certain compact support. That's the practical constraint I will impose when I design my filter. And now find me the values for this filter that preserve orthonormality, and also find me the best quality of compression of my signals, for example. So that's the Dobeshiz wavelet. Actually, I plotted the scale function twice. So here normally it's the wavelet function, it looks slightly different. What I wanted to show you is that one of the key difficulties that Dobeshiz had to solve when she was working on discovering such wavelet functions is that there's no analytical solution that she came up with for the description of this scaling function. In fact, one of the, part of the genius of Dobeshiz was that she found an iterative procedure to start with a certain function and progressively refine it so as to make the moment vanish and preserve the compactness of the support. Okay, and in the end, if you really want to find the Dobeshiz wavelet with 2 vanishing moments, 3, 4, etc., you'll have to look up the coefficients in a book, for example, or on Wikipedia, but you'll find the actual numerical values up to a certain precision. Okay. So I was mentioning briefly compression, and one of the key elements that make wavelet decomposition so interesting is how the compactness of the support enables so a certain sparsity in the way we capture local variations. So for example, if I take a look at the picture, the linear picture here, these edges represent very sharp variations in the image. What is nice is that typically they will be captured by the wavelet coefficients that correspond to that zone of the receptive field of the decomposition. And so what I could do is say, I'm going to devise an optimal basis in the wavelet domain to represent these images with as little a smaller number of coefficients as I can. So I do that, and then I can plot effectively which elements in the wavelet decomposition are most salient when I compress them with what influenced the design of the JPEG 2000 algorithm. What's interesting is that instead of having these Fourier representations that are impossible to represent in, for us visually, in their primal domain, here in the primal domain of the decomposition, really in the wavelet domain, we're able to plot the coefficients and see that they indeed look very much like the salient elements of the images as we look at the image, for example, as humans. Okay, so here we see how the hat is accounted for, and how, for example, for this monkey, there is a whole level of decomposition that is just concerned with the fur. Okay, so here, this is in 2D the counterpart to the fact that as you have a certain stride in the orthonormal wavelet decomposition, at each level of decomposition, you have fewer pixels. Okay, so in 1D we had this picture here. Okay, so I have fewer pixels to describe my time series. In 2D, you could in fact just shrink the image. Okay, and you can use these dyadic trees to represent at the same time the coarsest level of description of the image and then the finest levels. Okay, so the biggest images here correspond to the wavelet coefficients that represent the finest level of the finest elements of the image. What is kind of cool is that all of this remains really interpretable. What is also pretty extraordinary is how, for example, for these boats, so these cables here that are very small and singular elements in the picture are accurately represented in the wavelet decomposition. Try to account with such an, basically with a direct function with a Fourier basis. This is not going to work out so well for you. Okay? Yeah?
But isn't that just basically a high-pass filter which does edge detection?
Yeah. Okay? That's, I don't know where I plotted this. Okay, it corresponds to this picture. That's a very good remark. Yes, thank you. So to a certain extent, it's still interpretable, and also we could use that as a feature in a machine learning pipeline. All right? What is nice is that this prefactorizer here is fast to compute and also orthonormal, so it preserves all the information. So lately, there's been a resurgence of this theory of multiscale decomposition in deep learning, and in particular for computer vision. In time series, I think that there is still a bridge to build, basically, to leverage the same kind of nice properties that wavelet decompositions have in conjunction with having complex neural models. And so the way this was leveraged in computer vision is as follows. So we have a postdoc here, so Fisher Yu, who came up with the idea that to be able to do segmentation on images, and by the way, segmentation is also super important in time series analysis, we may want to have a neural network that is able to represent the image at different levels of coarseness, okay, with more or less, with finer or coarser pixels. And so the kind of segmentation he got was very high quality, although it was just a convolutional filter bank, so something simple and typically less time consuming than other segmentation algorithms. So that's comparison with other solutions that other people came up with, and that's their solution, so the multiscale representation.
Is it using wavelet?
Yeah, I mean, it's using a dilated filter bank, a dilated convolution filter bank, which is furiously similar to the dilated filter banks we use in wavelet decomposition. And actually, if you read the paper, they indeed introduce this inspiration. I mean, they indeed reveal that they had this inspiration, or at least that there is this similarity with what was developed in the 80s, 90s as multiscale decomposition of signals for time series and also visual understanding for compression mostly. And so that's the kind of segmentation they got after some preprocessing. You can see that you get a very good result, basically. And one of the advantages of the multiscale aspect of the neural network is that well, it enables it to have a full level, a level of understanding at on the entire extent of the image, which contrasts with some classifiers. So for example, if you take a look at neural networks that work on the ImageNet dataset, they typically pre-segment the images, and for that they use a separate algorithm that can be, in fact, fairly time-consuming. And then they take each of the sub-pictures in which there could be an object, and they apply classification to these pictures. Here it's different. We don't have such a separate, basically, segmentation task or detection task for the image. We have a full scenic understanding at the same time. That's one of the byproducts of being able to represent an object at different scales of representation. Incidentally, these dilated convolutions were also instrumental in speech synthesis. It's a bit paradoxical because typically when wavelets were used to process speech, which is typically what John Benedetto has done. So he's a very famous researcher who built basically one of the first pipelines that was a great speech interpreter based on wavelet theory. So here you more have the speech on the side of the input and then the text on the side of the output. In the WaveNet example, it's the reverse. We take the text as input and we generate speech. Okay. That's only elements now that show you that there is a certain level of resurgence of this fairly old theory. There's a lot to be done still, and one of the nice aspects of this wavelet basis is really that all the computations are useful. There is a lot of evidence today that as you build unstructured neural networks, there is a lot of the work they do that is really redundant. So if we manage to eliminate that, there's higher hope that we'll be able to apply, to use such networks as part of embedded devices or speed up the training time and so on and so forth. Incidentally, sorry, it's O of T log T here. We got an algorithm to decompose time series that's faster than FFT and to a certain extent better, more able to capture irregular and non-stationary signals, which is a great byproduct of the wavelet decomposition. Do you have any questions? No? So next week, we'll have the two last lectures that are a bit more theoretical, such as these ones. They will be, I think, less complicated than the wavelet theory. The first one will be about long memory processes and how you should be extremely wary of processes that have a long range, that are long range dependent. They can completely mess up your estimation procedure, and that's where basically the law of large numbers is going to break. And so we'll see where that leads us and the problems that generate and also how to solve them. And next Thursday we'll see another lecture that will try to introduce you to how to model irregular sampling in time series. And so, for example, a series of events. So the fact that there is a certain press release, or at a high frequency on stock markets, the fact that someone is trading, for example. And here the difficulty is that the time series will not be really about the values. The values are all one. We just say, well, an event is happening. The problem will be to map these events on the axis of time. And so basically guess the timestamps at which future events are going to occur. And that's important for high-frequency trading, for example. It's important for a much more, concerning field of time series analysis. A much more concerning class of phenomena. So typically, that's how you can use models. That's how you can build models that predict how many replica there will be to a certain earthquake. So that's how these models were created. They were created by Japanese and new researchers from New Zealand, mostly to be able to have models that could predict when earthquakes are going to happen, in particular subsequent earthquakes after a major one. So I hope that you'll enjoy these lectures. Thank you. Hi. Sure. By the way, I'm not sure in which group are you?